Good morning, children. Welcome to the class Complex Numbers Part 3. In this class, we solve some problems. The first problem: find the locus of Z such that mod Z plus 3 whole square minus mod Z minus 3 whole square is equals to 15. Here is the solution. Here Z is a complex number, so let Z is equals to x plus iy. Take mod Z plus 3 whole square minus mod Z minus 3 whole square is equals to 15. This implies mod Z is x plus iy. So x plus iy plus 3 square minus x plus iy minus 3 whole square is equals to 15. This implies mod x plus 3 plus iy whole square minus x minus 3 plus iy whole square is equals to 15. So this implies x plus 3 whole square plus y square minus of x minus 3 whole square plus y square is equals to 15. See, minus into plus minus, so minus y square plus y square get cancelled, and this is a plus b whole square minus a minus b whole square, which is 4ab. So this implies 12x is equals to 15. This implies x is equals to 15 by 12. So 3 5s are 3 4s are, which is equals to 5 by 4. So x is equals to 5 by 4, which is a straight line. Next problem. Second problem. Find the locus of Z such that mod Z square plus mod Z minus 1 whole square is equals to 3. So the procedure is similar to the earlier problem. Let Z is equals to x plus iy. Now taking mod Z square plus mod Z minus 1 whole square is equals to 3. Simply substitute Z is equals to x plus iy in this equation. So mod x plus iy whole square plus x plus iy minus 1 whole square is equals to 3. So this implies x square plus y square plus, this is mod x minus 1 whole square plus y square is equals to 3. So this implies x square plus y square plus x minus 1 whole square is x square plus 1 minus 2x plus y square is equals to 3. Here x square plus x square is 2x square, 2x square plus y square plus y square is 2y square, 2y square minus 2x minus 2x and 1 minus 3 which is minus 2 is equals to 0. So here 2 can get cancelled. So x square plus y square minus x minus 1 equal to 0. So here the locus of z is a circle. So which is a circle? Which is a circle. Here the third problem. Find the locus of z. Find the locus of z such that mod z plus 1 whole square plus mod z minus 1 whole square is equals to 4. Solution. The procedure is similar to the earlier problem. Let z is equals to x plus iy. Now take mod z plus 1 whole square plus mod z minus 1 whole square is equals to 4. In the place of z, substitute x plus iy. This implies mod x plus iy plus 1 whole square plus mod x plus iy minus 1 whole square is equals to 4. This implies mod x plus 1 plus iy whole square plus x minus 1 plus iy whole square is equals to 4. So this implies x plus 1 whole square plus y square plus x minus 1 whole square plus y square is equals to 4. Here plus y square which gives 2y square plus a plus b whole square plus a minus b whole square. So which is 2 into x square plus 1 square is equals to 4. So here 2, this is 2. So x square plus y square plus 1 minus 2 is equals to 0. So this implies x square plus y square is equals to 1, which is nothing but 1 square. So which is a circle, center at the origin and the radius r is equals to 1. So which is a circle, center at the origin and radius r is equals to 1. The fourth problem. Find the value of value of 1 plus I whole to the power of 20, 20 by 1 minus I whole to the power of 2018, provided I square is equals to minus 1. Solution. This expression can be written as 1 plus I by 1 minus I whole to the power of 2018 into 1 plus I whole square. So this is equals to 1 plus I by 1 minus I into, in the denominator it is a complex number. So reducing or converting this expression into complex form, we have to multiply and divide by the conjugate of the denominator. So 1 plus I by 1 plus I whole to the power of 2018 into 1 plus I whole square, which is A plus B whole square. So 1 plus I square plus 2I. Here 1 plus I into 1 plus I, 1 plus I whole square, A minus B into A plus B, A square minus B square. So 1 plus I whole square by 1 square minus I square whole to the power of 2018 into I square value is minus 1. So 1 minus 1 plus 2I. Minus 1 plus 1 get cancelled. This is implies 1 plus I whole square. It is 2I by I square value is minus 1. Minus into minus plus 1 plus 1 is 2. 2 whole to the power of 2018 into 2I. 2 get cancelled. This implies I to the power of 2018 into 2I. This implies I square whole to the power of, this is 1009 into 2I, which is equals to I square value is minus 1. I square value is minus 1. Minus 1 whole to the power of 1009 into 2I, which is 1009 is odd number. Minus 1 whole to the power of odd number is minus. So minus 1 into 2I, which is minus 2I. The next problem, fifth one. If 3 plus I is a root of x square plus ax plus b equal to 0, then find the values of a comma b. See, if 3 plus I is a root of this quadratic equation, automatically the conjugate of 3 plus I, which is 3 minus I, is also a root of this quadratic equation. So solution, let alpha is equals to 3 plus I, then beta is equals to 3 minus I. So x square plus ax plus b is equals to x minus alpha into x minus beta. So this implies this is equals to x square minus of alpha plus beta into x plus alpha into beta equal to 0. Here alpha plus beta is equals to 3 plus 3, which is 6, and alpha into beta is equals to a plus b into a minus b, which is a square minus b square. So 3 square minus I square value is minus 1, minus into minus is plus, so 9 plus 1, which is 10. Substituting alpha plus beta value and alpha into beta value. So this is equals to x square minus 6x plus 10. Therefore, a is equals to minus 6, b is equals to 10. Therefore, a is equals to minus 6, b is equals to 10. Next problem. Sixth problem. If 1, z1, z2 dash dash zn minus 1 are the nth roots of unity, then find the value of 1 minus z1 into 1 minus z2 into dash dash into 1 minus zn minus 1. Solution 1 z1 z2 dash dash zn minus 1 are the nth roots of unity. It is given. So z is equals to 1 to the power of 1 by n. This implies z to the power of n minus 1 equal to 0. Z values 1, z1, z2 and so on, zn minus 1. If 1 is a root of this equation, z minus 1 is a factor. If z1 is a root of this equation, z minus z2 is a factor of this equation. Therefore, z to the power of n minus 1 is equals to z minus 1 into z minus z1 into dash dash into z minus zn minus 1. So this implies z to the power of n minus 1 is 1 to the power of n by this z minus 1 as denominator, z minus 1, which is equals to z minus z1 into z minus z2 into dash dash z minus zn minus 1. Now taking the limit as z tends to 1, limit of z to the power of n minus 1 to the power of n by z minus 1 as z tends to 1. So taking the limit as z tends to 1 on both sides. So this is equals to limit as z tends to 1, which is z minus z1, z minus z2 and so on, z minus zn minus 1. So this is a standard limit, x to the power of n minus a to the power of n by x minus a as x tends to 1, which is n into so this implies n into 1 to the power of n minus 1, which is equals to, as z tends to 1, this expression becomes 1 minus z1, 1 minus z2 dash dash into 1 minus zn minus 1. Next, seventh problem. If z is equals to x plus iy, such that z bar whole to the power of 1 by 3 is equals to a plus ib, then find the value of 1 by a square plus b square into x by a plus y by b. X by a plus y by b. Here is the solution. Z is equals to x plus iy. This implies z bar is equals to x minus iy. Z bar whole to the power of 1 by 3 is equals to a plus ib. This is given. This implies z bar is equals to a plus ib whole to the power of 3. Z bar is x minus iy. This implies x minus iy, which is equals to a plus ib whole to the power of 3. So this is equals to a plus b whole cube, a cube plus 3a square ib plus 3a I square b square plus ib whole cube. So this is equals to a cube, I cube into b cube. I cube value is minus I. So minus I b cube plus this is 3I a square b. Here I square value is minus 1. So minus 1 into plus. So minus 3a b square. So this is equals to a cube minus 3ab square minus I is common b cube minus 3a square b. Now comparing the real and imaginary parts on both sides. So equating real and imaginary parts on both sides. X is equals to a cube minus 3a b square. This implies a is common, and again writing as denominator, x by a is equals to a square minus 3b square. So this is regarding the real part. Now what about the imaginary part? So y is equals to b cube minus 3a square b. b is common in this expression, so writing as denominator, so y by b is equals to b square minus 3a square. So this is equation 1 and this is equation 2. Therefore 1 plus 2 implies x by a plus y by b is equals to a square minus 3a square, which is minus 2a square. Again minus 3b square plus b square, which is minus 2b square. So this implies 1 by a square plus b square into x by a plus y by b is equals to minus 2. Next problem, 8th problem. If z is equals to 1 plus I into 1 plus 2i into 1 plus 3i lie on the circle with center at origin and radius r. Then find the value of r square. So solution. See, z is given as 1 plus I into 1 plus 2i into 1 plus 3i. So product of 2 or more complex numbers is again a complex number. So z is a complex number. This complex number is lying on the circumference of the circle with center, origin and radius r. Then we have to find r square value. R square value. Since mod z is equals to r is complex form of the circle center with origin and radius r. So this is the known concept. So what is given? Z is equals to 1 plus I into 1 plus 2i into 1 plus 3i. Taking mod on both sides, mod z is equals to mod of 1 plus I into 1 plus 2i into 1 plus 3i mod is equals to r. So since mod z1 z2 is equals to mod z1 into mod z2, so this is implies mod z is equals to mod 1 plus I mod 1 plus 2i mod 1 plus 3i is equals to r. So this implies taking square on both sides. So this is root 2 into root 5 into root 10 is equals to r. This implies taking square on both sides. So r square is equals to 2 into 5 into 10. This implies r square is equals to 100. R square is equals to 100. Next problem. Ninth problem. Find the minimum value of mod z minus 1 plus mod z minus 5. Find the minimum value of mod z minus 1 plus mod z minus 5. Solution. Since mod z1 minus z2 is always less than or equal to mod z1 plus mod z2. This is a known principle. It is an inequality. Therefore, R mod z1 plus mod z2 is greater than or equal to mod z1 minus z2. So put z1 is equals to z minus 1 and z2 is equals to z minus 5. This implies mod z minus 1 plus mod z minus 5 is greater than or equal to mod z minus 1 minus z minus 5. So here minus z plus z get cancelled. Minus of minus 5 which is plus 5. 5 minus 1 is 4. So mod z minus 1 plus mod z minus 5 is greater than or equal to 4. Therefore, the minimum value is 4. The mean value is 4. The minimum value is 4. Next, 10th problem. If mod z1 mod z2 is equals to 2, mod z3 is equals to 3, and mod 9 into z1 z2 plus 4 into z1 z3 plus z2 z3 is equals to 12. Then find the value of mod z1 plus z2 plus z3. Solution. Here what is given? Mod z1 is equals to 1, mod z2 is equal to 2, mod z3 is equals to 3. And such that mod of expression, so and so expression is equal to 12. Then we have to find mod of z1 plus z2 plus z3. Mod z1 is equals to 1, taking square on both sides. Mod z1 square is equals to 1 square, which is 1. This implies mod z square is z into z bar. Mod z square is z into z bar. So here mod z1 square is z1 into z1 bar is equals to 1. Similarly, mod z2 is equals to 2. This implies squaring on both sides. Mod z2 whole square is equals to 4. This implies Z2 into Z2 bar is equals to 4. Similarly, Z3 mod Z3 is equals to 3. This implies mod Z3 whole square is equals to 9. This implies mod Z3 whole square is Z3 bar which is equals to 9. So now taking mod 9 Z1 Z2 plus 4 Z1 Z3 plus 1 into Z2 Z3 is equals to 12. In the place of 9, in the place of 4, in the place of 1, substitute Z3 bar, Z2 bar, Z1 bar, 9, 4, 1. So this implies mod Z3 bar, Z3 bar into Z1 Z2 plus in the place of 4 Z2 bar. So Z2 bar into Z1 Z3 plus in the place of 1 Z1 bar. So Z1 bar Z2 Z3 is equals to 12. In the left hand side mod Z1 Z2 Z3 Z1 Z2 Z3 Z1 Z2 Z3 is common. So this implies mod Z1 Z2 Z3 into Z3 bar plus Z2 bar plus Z1 bar is equals to 12. We know that mod Z1 into Z2 is equals to mod Z1 into mod Z2. So this is implies mod Z1 mod Z2 mod Z3 into mod Z3 plus Z2 plus Z1 whole bar is equals to 12. Mod Z1 is 1. So 1 into 2 into 3 into mod Z1 plus Z2 plus Z3 whole bar is equals to 12. Is equals to 12. One into 2 into 3, which is 6. So this implies 6 into mod Z1 plus Z2 plus Z3 whole bar is equals to 12. This implies Z1 plus Z2 plus Z3 mod whole bar is equals to 2. 6 1s are 6 2s are. So conjugate of conjugate or taking conjugate on both sides. Taking conjugate on both sides. So conjugate of a complex number is the complex number Z1 plus Z2 plus Z3, and the conjugate of a real number is again a real number. So 2 is 2. So with this we conclude this class. In the next class we see some more problems. Thank you.